something hard to metabolize kernel PCA. Okay, for today's finish, we need something which is easier to metabolize maybe. So we have one further measure here, which are the so-called Fischer phases. But once again, what are we doing here? We do feature reduction, meaning that we try to come up with new features that gives us, or that give us hopefully an easier time, a less hard time to look for for patterns. Yeah. So the example of the kernel PCA here is a good example, because here in the original data space we have a hard time to find the corresponding pattern here, the reds and the blues. Yeah. But with the derivation of new features, in that case with the kernel PCA here, we have much less hard time to find patterns here in this new feature space. So that is the key idea of feature reduction again. Yeah, so we want to come up with new features that are better suitable for finding some patterns. Yeah, where it is simpler to find patterns. So the new representation is somehow more rich. Yeah, and here kernel PCA is just one way to do it. Obviously, yeah, it's not the one fits all solution, but it's one way to do it, and that's maybe a very good example of the general idea what we're doing here. So now Fischer phases here is a supervised measure or method. So PCA, kernel PCA, SVD, and stuff like that is all unsupervised. This one here is supervised. So we use our training set and try to find representations or representation features that increase the discriminative power in the new feature space. And we actually look at two different things. We try to minimize the similarity between objects from different classes. Okay, sounds good. That is the so-called between class scatter matrix, denoted by sigma b. And for that case, we just use the covariance matrix of the class centroids, yeah, of all the class centroids. Yeah, so we compute the centroids of all classes and then compute the covariance matrix of these class centroids. We need to have multiple classes, of course, in order to be stable. If we only have a couple of classes, then maybe we use more than the class centroids in order to get stable covariance matrices. But anyway, so what do the covariance matrices of the class centroids tell us? Those are they model the matrix models obviously the directions in which the class centroids or the classes can be separated. Yeah, so we need to have high variance along these directions here. So we have to maximize, so to say, these directions that are displayed in this covariance matrix here. Yeah. And on the other hand, if we look at the within class scatter matrix, where we try to maximize the similarity between objects in the same class, so we use for this within class scatter matrix, which should display the directions for the within class distances. So these directions should be kept small somehow, and for that scatter matrix we use the average covariance matrix of all classes. Yeah? So once again, those are the directions for the in-between classes, between the classes. So we want to maximize these directions, and these are the directions for the within class distances or similarity. So here we want to minimize these directions, and in the end we want to have a new basis. Yeah, so we look for new basis vectors. And these basis vectors should be basis vectors, so that means that they should be pairwise orthogonal, yeah, perpendicular to each other. So that is the side constraint here. And once again, the between class scatter matrix, the directions between the classes should be high or higher weighted, and the directions within the classes should be lower weighted. Yeah, so this thing up here should be maximized, and this term down here should be minimized. So we just take the ratio of those two things and maximize this ratio. Yeah? Meaning that we try to maximize the directions that helps us to distinguish between the classes, and minimize the directions that help us to be in the same class or within the class, so to say. Yeah, so that is the basic idea of Fisher phases, and that's basically all. Yeah, so as simple as that, if you take it simple. Yeah, but anyway. So some remarks. The vectors having the largest eigenvalues, of course, correspond to the normal vector of the separating hyperplane in the so-called linear discrete analysis, or also Fisher's discrete analysis. I have a problem with the M here, so maybe that is also content of KDDM. Linear discrete analysis or Fisher discrete analysis. There is a kind of linear model close to support vector machines, and yeah, so we have separating hyperplanes here in these linear models, and this is the relationship to these Fisher phases here. Fisher phases are limited because we assume that we have monomodal classes, so each class is assumed to follow one Gaussian multivariate Gaussian distribution. Yeah, that's why we model that with these covariance matrices here. Yeah, the covariance matrices obviously are one of the Gaussian one parameter of a Gaussian model. Yeah, and the other one are obviously the means, so the centroids here. Yeah, that's fine. Okay, so we obviously assume that each of the class follows one multivariate Gaussian distribution, and that we can somehow adjust or find the basis, the new basis based on these Gaussian distributions. Yeah? Multimodal or non-Gaussian distributions cannot be modeled well because it's so there's no extension to multimodal or non-Gaussian distribution. So we always rely on this monomodal Gaussian assumption. If that assumption doesn't hold, we may have anything, so to say. Yeah. And yeah, there are many variants of this basic Fisher phases called relevant component analysis, large margin nearest neighbor approach, and stuff like that. So they somehow extend that a little bit, but not in the terms of multimodal or non-Gaussian. Yeah, just that you know. Okay, and yeah, so the idea is pretty simple. And once again, you see that all of those things here rely on different assumptions. Yeah, Fisher phases rely on different assumptions. Multimodal, monomodal Gaussian distributions. Kernel PCA relies on specific assumptions. So first of all, PCA relies on specific assumptions. We look for the directions of highest variance because they are more interesting, more helpful for discriminating between patterns. Kernel PCA relies on the same assumption and needs a good guess for the kernel function. Yeah. And so on and so on and so on. Yeah, so we have a lot of assumptions behind all those pre-processing steps. Always keep that in mind. So here's a short summary. Yeah, we had linear basis transformations that may yield a rich framework to optimize feature spaces. Unsupervised methods try to delete low variant dimensions, what we just said. Yeah, PCA, SVD, they look for the high variant dimensions, for the high variant directions by linear basis transformations. Kernel PCA extends the PCA for nonlinear kernel spaces. Once again, the basic assumption is the direction of highest variance is the most interesting, are the most interesting directions for the data mining and the machine learning task. If that's not the case, forget about all that stuff here. Yeah, and we also saw Fisher phases here that are supervised methods that try to minimize, of course, again, the within class distances, and in parallel, typically maximizing the between class distances. So Fisher phases and variants do exactly like that, because, of course, if we know something about the data, like training data, then, of course, we can use that information to not just so blindly look for the direction of highest variance in that case. Yeah? Okay, so Fisher phases, of course, guide the search for good features more from the training set than from just the assumption of high variance. Yeah, here's some further readings if you want to dig in deeper a little bit more. Yeah, so that was everything for this week. So yeah, a lot of stuff again to metabolize. I hope you can do that. And yeah, Stay healthy as always, and talk to you next week. Bye bye.